In 2.5, we looked at proofs involving equations and going from the start of an equation, what you're given, through solving the equation and justifying every step along the way. So we're going to keep going along that vein, but now we're going to start looking at proving that certain things in pictures that you see here or other things about certain statements, we're going to prove that those are true. So a proof is a logical argument that shows that a statement is true. In this class, we're going to be dealing with something called a two-column proof. So it has numbered statements and corresponding reasons. So the first column is the statements that we're making, and the second column is the reasons for each of those statements. So the reasons, or the statements that we have on the left side are going to be either things that we were given as true, or statements that we got from the given statements. So we take the given statements and we go from that to something else. That's the type of thing that we're going to have on the left side. And then again, the right side is just a justification for each step as we go through. In example 1, we're looking to prove that the measure of angle EBA, that's going to be this angle here, is congruent to the measure of angle DBC. That's going to be this angle in green. So we're trying to prove that those two, the red angle and the green angle, we're trying to prove that those are the same, that those are equal to each other. So we start off with what we were given. We were given that angle 1 is equal to, the measure of angle 1 is equal to the measure of angle 3. So that's these two outer angles, angle EBC and angle DBA. So we're given that those two are the same. Now, generally what we're going to do as we go through this proof is what we're going to say is that angle 2, so this double marked angle, that one is shared by both of the angles in question. Both the green angle and the red angle have that piece in it. And the other piece of those angles are angles 1 and 3, which are congruent to each other. So basically what we're going to say is that each angle has kind of two parts to it. One of the parts is shared between the two angles, and then the leftover part, although they're different in each angle, they are congruent to each other. That's angles 1 and angles 1 and 3. Those are the same as each other. So that's generally how this proof is going to go. So we start with what we're given. We're given that the measure of angle 1 is equal to the measure of angle 3. Well, let's see if we can come up with some statements that describe the angles in question, the red angle and the green angle on there. So that's angle EBA and angle DBC. Well, we could say that angle EBA is made up of angles 2 and 3. So let's make a statement that says that. And we can make a statement like this that says that the measure of angle EBA is the sum of the measures of angles 2 and 3. So if we put angles 2 and 3 together, we get the measure of angle EBA. And we can do that because of the angle addition postulate, which just says that if you put two angles together, then the total measure of the combined angle is just the sum of the two individual angles. And we can do the same thing for angle DBC. Now at this point, we want to look at our given statement because we're going to use this. So we know that this statement right here is true. So the measure of angle 2 is equal to the measure of angle 3. So what we could do is we could take this statement and we could substitute. So we could say if we know that the measure of angle 3 is really the same as the measure of angle 1, we could just take the measure of angle 1 and plug it in there. So that's what we're going to do for statement 4. And this is what we get. So we took the blue statement, which is that the measure of angle EBA is equal to the measure of angle 3 plus the measure of angle 2. But we know that the measure of angle 3 is really the same as the measure of angle 1. So we can just replace the measure of angle 3 with the measure of angle 1. And that's what we did here in step 4. Well, now if you look at this, you can see that both of these are the same. So we have the measure of angle DBC is equal to the measure of angle 1 plus the measure of angle 2. And that EBA is the measure of angle 1 plus the measure of angle 2. So both of these angles must be the same. So we can use the transitive property to say that if the measure of angle DBC is the same as angle 1 plus angle 2, and angle 1 plus angle 2 is the same as the measure of angle EBA, then the measure of angle DBC and the measure of angle EBA, these two must be the same as well. So that's what step 5 is. And there you have it. On step 5, we have proven what we were looking to prove. We have proved that the measure of angle DBC and the measure of angle EBA are in fact the same thing. So if you remember back a few sections, we started with postulates or axioms. These are things that are not proven to be true. They're things that we look at and say, yeah, that's true, or just accept that it's true, so that we can do geometry. Once you have a set of accepted postulates or axioms, then you can use those to prove certain things are true. And when you use those to prove something is true, we call that a theorem. So a theorem is a statement that can be proven. It is actually indeed true. And we know it's true based on the postulates or theorems that we come up with. All right, let's now look at some properties that we have. So the first property we're going to look at is called the reflexive property. We've looked at this before in section 2.5, but we're going to look at it again here. So for any segment, call it AB, we can say that that segment is congruent to itself. So all this is really saying is that this object, or any object, is the same as itself. We can do the same thing if we look at theorem 2.2. We can do the same thing for angles. So we can say angle A is the same as angle A. This is basically just like saying 5 is equal to 5. Something is the same as itself. Again, this may seem like a strange property to have. It may seem like we don't really need to state that something is the same as itself. But when we're doing proofs, we need to be very, very thorough as we go through and make sure that everything that we say is entirely justified as we go step by step through the proof. So in proofs in mathematics, we do not leave any ambiguity whatsoever. We are always very, very clear about every single step that we do so that no one can argue against the proof that we have because every single step is justified. Okay, again, symmetric property. As we continue on here, symmetric property just says that you can take an equation or a congruent statement and flip it around. So if segment AB is the same as segment CD, then we can say that segment CD is the same as segment AB. And we can do the same thing with angles. So we could say if angle A is congruent to angle B, then angle B is congruent to angle A. It doesn't matter which side of the congruent symbol or equal sign that things are on. And then the transitive property deals with the fact that you have two equations or two congruent statements that have one side of them the same, one piece is the same. So if AB is the same as CD and CD is the same as EF, then AB must be the same as EF. That must be true. Because if two things are the same as something else, then those two things must be the same thing. And we can do the same thing with angles. All right, let's look at some properties here, name the property. So if angle R is congruent to angle T and angle T is congruent to angle P, then angle R must be congruent to angle P. So here we have R is the same as T and T is the same as P. So that means R must be the same as T, the same as P. That is the transitive property. All right, if segment NK, this is part B, segment NK is congruent to segment BD, then segment BD is congruent to segment NK. This is the symmetric property. So saying that we can flip a congruent statement around and we get a true statement still. All right, let's look at another proof. So in this lesson, most proofs involve showing that congruence and equality are equivalent. You may find that you are asked to prove something that seems obviously true. It's important to practice writing these proofs so that you'll be prepared to write more complicated proofs later in the chapter. So I've mentioned things like this before. It may seem like some of the things we do here are trivial or that they don't really need to be said, but it's important that we get used to laying out step by step every single thing that we do and justify every single step, because as we get into more and more complicated proofs, it's going to be very important that we are doing that to make sure we're very clear as we go through the proof. All right, let's set up this proof. All right, so the first step of every proof that we do is going to be what we are given. So statement one, we start with what we're given. We're given that M is the midpoint of AB. On the right side, you can see a picture of what's going on here. So point M is in the middle of segment AB. More specifically, it is exactly in the middle. It is the midpoint, which means that M bisects the segment. Again, the word bisect, Bi means two. Sect, think of like sections, two sections, but more specifically, cut exactly in half into two equal sections. So that means that AM is really the same as MB. And that's what those two green marks mean. So segment AM is the same as segment MB. So what we can say then is just that. We can say that those two segments must be congruent. And we know that that must be true because that's what it means for point M to be the midpoint. So that's going to be step 2. Once we've said that these two segments are congruent to each other, we can say that the lengths of those two segments are equal to each other. That's what it means for segments to be congruent. It means that they have the same length. So that's going to be step 3. So again, when you have something like segment AM, so AM with a line written above it, or the segment written above it, that's talking about the object itself, that this segment is congruent to this segment. And then in step 3, we have just the letters A and M is equal to the letters M and B. Remember, that means the distance between A and M is equal to the distance between M and B, or the lengths of those segments. Okay, now that we have lengths written down, we can start making conclusions about, kind of similar to what we did with angles, saying that one segment is equal to two different segments added together. So that's what we're going to do here. So we can say that the length of AB, so the distance all the way from A over to B, is equal to segment AM plus segment MB, the length of those two segments added together, I should say. So there we have it said that the length of AB from A all the way over to B is equal to those two pieces that it's cut into added together. So we take the distance from A to M and the distance from M to B, add those together, we get the distance from A to B. And again, that's the segment addition postulate, just telling us that if we add segments together, we get the length of the entire segment, the combined segment. All right, 2 more steps. So what we can do now is we can combine steps 3 and 4 together. So we know that AM is equal to MB. And so what we can do is we can say, well, in this statement, in statement 4, AB is equal to the length of AM plus the length of MB. Well, MB is really equal to AM, so let's substitute that in, and then we'll get a statement that we can simplify down to what we were trying to prove. There it is, step 5. So on the right side of the equation in step 5, you have AM plus AM. Well, if we combine like terms there, that's 2AM, and so then we will get the statement that we are trying to prove. So when we combine like terms there with the AM and the AM, putting those together to get 2AM, that brings us to the statement that we were trying to prove. So that proves that the length of a segment is twice the length of the distance from one end to the midpoint. So that's what AM is, the distance from one end of the segment to the midpoint. And so the whole segment is twice that length. So we've just proven that that is true.